So you know, Paul, this whole extragalactic distance scale hierarchy is a real mess. You know, it's kind of almost embarrassing.
A lot of things to go wrong in there.
Yeah, it's really, really not good. What we really need is a way from going from our own galaxy to other galaxies, big galaxies, using a geometric method like parallax that we do to the nearest stars, but in one step, and getting rid of all these little rungs where, quite frankly, we could easily slip off and hurt ourselves, get the wrong answer.
And it turns out that there is a method just being developed in the last decade or so, which has a lot of promise for us. And this is actually using masers. Now, you're probably familiar with lasers. You have them in your DVD players and fiber optic communications and everything. Masers are basically the same, only it's at microwave wavelengths rather than visible light. And let's just remind ourselves of how these things actually work. The basic idea behind a laser or a maser is that you have energy levels. In the case of a maser, they're molecular energy levels. In the case of an atom, they're atomic energy levels, but that doesn't really matter. And electrons can be in, or the molecule can be in different states here. And what you need to make a laser or a maser work is what's called a population inversion. Normally all the electrons or energy states will be down at the bottom level.
Yes.
But if for some reason, maybe you're zapping something with energy or heating it up or something, you get large numbers of atoms in the top state.
So you get more in the top state than the bottom state.
Yes.
Yep.
Then if you get a photon coming along from outside which has just the right energy that's equivalent to this energy level gap, it will come along and it will actually trigger, stimulate the electron or the energy state to jump down.
Right, so that's called stimulated emission, because when it drops down, it'll emit a photon.
Yes. And what that means is instead of getting one photon with this energy, you get two. But the really important thing is they're perfectly in phase with each other. They're perfectly lined up, perfectly in the same direction. And so if you can have a long enough progression of this, whatever it is that's in this population inversion, a photon can turn into 2, 4, 8, 16.
So you get a cascade, a runaway, almost like a nuclear reaction of photons. All you have to do is somehow excite and get all these things up in these high energy states.
And you need to have a long enough distance to go through. Now in a laser on Earth you normally have two semi-silvered mirrors on both sides. The light can bounce backwards and forwards many, many times.
Well, you say semi-silvered. You actually mean they're like 99.99%, and they only let a little tiny bit of stuff out at the either end, right?
Yes, that's right. I mean, fully silvered would be even better, but you want the laser to come out at some point. But you think this would be something you'd see in the laboratory. But it turns out these actually occur in space. And in particular, there's a small number of active galaxies which have incredibly strong maser emission, so-called megamasers, because of their incredible power, coming right from the center. It's not the whole galaxy, it's only from your dot in the middle.
Right in the center. So this is NGC 4258. It's a galaxy that is about 7 megaparsecs, so roughly 22 million light years in distance. And it's funny, it's one of the nearest objects that has a semi-active black hole in its core.
Yes, so it's got an active galactic nuclei. We talked about them in the previous course. What that means is there's a big black hole in the middle with a swirling disk of gas around it, and that gas is really hot as it swirls faster and faster around the black hole before forming in. And it seems that that central black hole and the disk around it is where this maser is coming from. Now if you take a spectrum of this, you find something like this.
So this is a radio spectrum, right?
That's right. Because this is a maser. It's coming out at microwave radio frequencies. So use a radio telescope. And what you can see is it's not just one emission line, it's a whole bunch. This is actually OH, water vapor. So there's clearly water in this thing, and it's being stimulated into the upper energy level and jumping down. But we see a whole series of very narrow spikes, narrow components at different positions and different velocities.
And these are at different times. This is going back in 1997 all the way up to 2000. So this is 3 years worth of data. And so we have different frequencies. And we know that masers emit things at a very precise energy level, that energy difference between the two levels. So we know what that is to, 7 decimal places or something.
Okay, so we seem to have a whole bunch of compact clumps moving at different speeds in the middle of this galaxy, emitting this water vapor maser emission. Now, because these radio emitting clumps are incredibly bright and incredibly small, we can use a technique that we can't normally use, which is called very long baseline interferometry.
Or VLBI, as we like to say.
VLBI, yes. And the way this works is you take radio telescopes, like this one at Parkes here in Australia, and normally a radio telescope has a pretty blurry image because of the diffraction limit. You can only see very blurrily what's going on.
Yeah, so remember that the diffraction limit in radians is the wavelength of light divided by the diameter of the dish. Very big dish, 70 meters here, but the wavelength of light we want to look at here is very long. It's on order of several centimeters, so that ratio isn't very big. Is quite big, so not very precise.
However, what you can do is you can combine different radio telescopes all around the world, and occasionally even in space, and for each radio telescope you can record the signal as it comes in. Now, radio waves, you can actually record the full phase of the signal. Optically, just count photons, so you can't do this at optical wavelengths without actually bouncing mirrors between the telescopes. But in radio, you can actually coherently record the signal with its full phase, usually on racks of DVD players or something like this. And then you can ship a box full of DVDs with a signal from one radio telescope to another one and combine them all. And they have devices called correlators that look for patterns by combining the signal from, say, a telescope in Eastern Australia, Western Australia, New Zealand, Japan, all around the world. And by combining the signals, as long as the thing you're looking at is incredibly bright and incredibly small, you can get absolutely amazing precision.
Because you're actually using the telescopes as a giant telescope with a lot of holes in between. So you can take the telescope, for example, at Parkes in Australia, combine it with one, for example, in South Africa or in Hawaii, and stare at the same thing, and then you end up essentially having a telescope that's 10,000 kilometers across instead of only 70 meters. So you've got a very, very big diameter of the telescope in the bottom, which means you get really, really amazing resolution, assuming the object is bright enough to be seen.
It means you can actually get micro arc seconds resolution, whereas you're lucky if you can get 1,000,000 times worse than that of an optical telescope. Yeah. So when this works, it doesn't work very often, but it does work for masers. You can get image sharpness. It's about 1,000,000 times better than you can achieve by any other technique.
Right.
So pretty amazing. And when they use it on this, they can map these dots around in the middle of this galaxy. And what you can see, this is a map on the sky, is they're in a kind of line. There's a bunch of redshifted ones on one side. These are moving away from us. A bunch that are not redshifted or blue shifted in the middle, and a blue shifted one on the other side. So it's kind of like a spinning disk. So you've got the blue side moving towards us and the red side moving away.
Okay. And then if we zoom in here, let's just get ourselves here. So we're going to look and we're going to zoom in here. And these things seems to be a small pattern of what's going on there, but not much. And these things actually do have an interesting pattern and another interesting pattern. So if we think of it as a disk, it's sort of a warped disk. It's not just a nice pancake.
And if we look at a position velocity diagram, so what we're plotting here is the velocity against the position. So these are the ones on the left, those are the ones on the right. And what you can see is velocities go up over here. In the middle they're going down as a straight line, and then it's something like this.
Right, okay, and that almost looks like a square root, which is what Kepler's law would predict if these things were rotating around a mass.
Yeah, so these ones out here on both sides are almost perfectly fitting what you'd expect if it's orbiting around the central black hole.
Right, so you can think you have this big disk with the hand, sorry, I'm off things, and so I'm rotating like that, so one's going to be coming towards you and one's going to be going away from you.
But in fact, the bits closer in have to move faster because they've got more
Right.
gravity to fight off, so that's rather hard. You have to move your shoulders faster than
Yeah,
your
that's
arms.
right, because I'm fixed, so I don't actually count as a gravitational system.
So in fact, the one's going closer and moving faster and faster.
Right.
How about these ones? What's going on there?
Oh, so those are the ones that are like the lighthouse going past you like that. And so when they're directly at you, there's almost no velocity. But then you pick up that sine curve, right? So,
Yes, they're moving sideways.
yep.
And so when they're bang in front, they're perfectly at right angles, so there's no velocity. A bit on one side, they're moving a little bit away or a little bit towards you.
Right, and so these things are moving so fast at 1,000 kilometers or 1,500 kilometers per second that you're going to pick up that little sideways motion just from the small little angle multiplied through.
Yeah, so it's what you've got is, for some reason, you've got this disk around the black hole, and there are clumps within this disk, and they're presumably being heated up because the whole disk is hot 'cause it's spiraling around a black hole, which is a pretty violent environment.
Yep.
And that's producing the population inversion, and hence the masers. But the masers aren't coming from all parts of the disk. They're coming from three very specific parts. You've got a line along the side here, where
Yep.
the lumps there are amazing, a line along the side there, where they're amazing, and the bit right in front of the black hole, where they're amazing.
Oh, okay. So
But the bits over here, for example, or over there are not amazing.
So it sort of makes sense, though. If you think about how a maser works, you need to have a photon be created, which is going to cascade to another one to give another 2, 4, 8. But you need those not to be redshifted, because if they get redshifted, they're no longer going to be able to stimulate the emission of the next object. So you need to have spots where there's not going to be any big redshift.
Yes, so you want, if a random photon is emitted by a cloud of gas, but it goes to another cloud of gas, that other cloud of gas is going to be at the same velocity along the line of sight. So here, because everything's moving perpendicular to the line of sight,
Yep.
that's the case. So you get a photon maybe even starts from near the black hole, that's very, very hot, and then every cloud of gas, they're all moving sideways at different speeds, but it doesn't give you a Doppler effect.
Right, so the Doppler effect is the sine of the angle away. The sine is essentially 0, and so the sine of 0 is 0.
So quite a small signal can get amplified and amplified and amplified as it goes along. But also here, along this line here, the gas is briefly moving straight towards us.
Right.
So that means once again you've got a whole bunch of gas. It's like the edge of a circle, which is at the same velocity. So once again there's amplification. Whereas if you're looking further forward, where it's curving obliquely, in that case, if the photon wants to go this way, it has to go through gas at different speeds, and so it won't get amplified very much. So probably there is maser emission coming from everywhere in the disk, but the maser emission from here is being beamed off in some different direction.
Right.
Only from here and here is being amplified in our direction.
In our direction. Okay, yeah, that makes a lot of sense.
Okay.
So, we have a beautiful system which looks a little complicated, but actually compared to most galaxies, looks rather simple. You have these curves that are sort of Keplerian, we think, and we have these objects in front that are moving. But the interesting thing, of course, is we know how far these things are apart. We know what the angular size is. And just like the eclipsing binary, I bet, since we're going to be able to measure the velocities and stuff, we're going to be able to convert that stuff to a physical size.
Well, there are two more things we have to measure, and these are things that we really need very long baseline interferometry to find. One is, we could look at the spectrum and we see all those spikes, and by looking over 10 years, we can actually see the spikes will change in wavelength quite measurably. The only reason we can do this is because they're masers. They're such very, very narrow spikes. With radio telescopes, you can get incredibly good spectral resolution, and so you can actually see the shift in velocity. And of course, shift in velocity is acceleration.
Ooh, and acceleration going in a circle is going to be v squared over r.
Yes. So particularly for the ones in front, you can see the change because they're accelerating towards the middle. The
Right.
acceleration is always centripetal. We should be able to see the change in velocity. So that's going to be a really crucial clue. The other really crucial clue is, again, for the ones in front, you can actually, if you observe from years apart, you can actually see them moving. Now, this is almost unheard of in any galaxy other than our own, to see the sideways motion. But you can actually, with the incredible micro-arc-second resolution of very long baseline interferometry, actually see as they're moving sideways and measure their sideways velocity.
So this sounds like a good time, Paul, to go and take the data and go through and try to see how we might measure the distance to this galaxy in detail.
So let's go look at all these different clues and try and put them together and see if we can actually get a distance.